This is Unit 4, Investigation 1, Lessons 2 and 3. We're going to start off with the entry ticket together. We're going to continue to be exploring polynomial functions using what we've already learned about linear, quadratic, and exponential functions. So we're going to be kind of working with factoring. It's basically the idea that you can take a polynomial from this is standard form, and turn it into factored form. The more that you're able to factor it, the easier it's going to be for you to graph it. So for example, first graph, I have -6, 0, and 0, 0 as my roots. So there's one of two options that I could do. And I also can see that it's concave up. So that means it's going to be positive. I also see that I can say, okay, well, I have x minus 0. That's how I can get that x 0, 0 intercept. And then we have times x plus 6. Because if I took x plus 6 and set it to 0, I would get x is equal to -6. So I'm going to change to green. And on this graph, I have -3 and 3 as my x-intercepts. So I know that I'm going to have, and the same thing, I have concavity that's positive. It's a smiley face, right? Smiling. And I know that this is going to be x plus 3, x minus 3. Here, I have -2 and +4, and I have downward concavity. All right, so I know that this is going to probably have a negative in front of it. And now I can say, okay, well, my function is probably going to be something along the lines of x plus 2 times x minus 4. And lastly, we have -3 and -2. And we know that this is upward concavity. So we're going to have x plus 3 times x plus 2. And that should be our graph. Now I'm going to go one step further and prove it to you. So I'm going to graph these exactly the same way that I color-coded them here on Desmos. So if I have x minus 0 times x plus 6, which actually another way you could have written it is x times x plus 6. X minus 0 is just x, so you could have also had this. And here's my graph. And you can see that it's exactly the same. You could even double check the vertex on this graph and the graph in your book. Now, if I graph x minus 3x plus 3, the same thing happens. I can look at all my all my points of intersection / my vertex points, and I can see that that matches exactly to this graph as well. The third graph, x plus 2, x minus 4, was in purple. And as you can see here, if I took out this negative, it would still be the same exact parabola, just it would be, instead of concave down, it'd be concaved up. So that negative that's in front is crucial because it completely changes that graph. Plus 3x plus 2, that's in black. And as you can see, you get that same exact x-intercept, and you get the same exact 0, 6 y-intercept, which you see right here. In the concept development, it gives us a polynomial and asks us to try to figure out an equation for it. So the first thing I'm going to do, and they actually give you some suggestions to the right here. But this, I have 3 different possible roots. So I have x minus 0, or another way to write that is just x, because x minus 0 is just x. And my other 2 roots are +2 and +3. So I'm going to have a -2 and an x minus 3. So it could be either this or this, doesn't matter which way you put it. And let's say, okay, let's see if this matches up with what I have in front of me. So here I've graphed it. So if I look at this line, I'm looking at my x-intercept 0, 0, 2, 0, and 3, 0. So all my x-intercepts are there. But the only thing that's wrong is the graph doesn't have the same concavity, it doesn't have the same end patterns. So I need to make sure that my graph is more specific. There's something missing from this function. So that's our job to figure out. That's our job for today. We're going to be doing this and going back to it. We're going to be taking these polynomials and analyzing the qualities that the graphs have. So I've taken the liberty of already graphing these 3. So we're going to go to Desmos here, and we're going to start with the first one, x minus 2 times x plus 5 squared. So I'm going to be what we're looking at here. If your margins get messed up, you can use your home button to get you back home. I'm going to zoom out a little bit here just so my view is a little bit better. And here I can see that, okay, I have a negative 5, 0 and a 2, 0 as my roots. That makes sense because those are where my x-intersects should have been. However, let's look at the pattern on these 2 points. So at negative 5, 0, if you kind of bring your attention over here, this has a degree 2, right? And here, as you can see, any type of degree 2 that we've ever graphed has been a quadratic, right? Which is a parabola. A quadratic, which is degree 2, will always give you some sort of parabola. So here, this makes sense that we have some sort of parabola. Now, if we follow the line and try to get to the next intersect, the x-intersect 2, 0, we see that here the line acts different. Instead of jumping off that line to make a parabola, kind of doing a little bouncy, right? It goes right through. So over here, it just goes right through the line. And if you can kind of see here, x minus 2, that's a linear function, right? So it makes sense that at that intersect, the line, that the polynomial will just be going right through that intersect as a straight line. I kind of want to bring your attention, I'm going to get rid of this one for right now, and I'm going to bring your attention to, actually before I do that, one last thing I want to say. If you look at this graph, it's kind of coming from like a downward area, and it's going upward. So it comes all the way up towards positive infinity. But pay attention to how the other graphs maneuver that same exact way. So now I'm going to be focusing on the black line. I'm going to get rid of my purple, and I'm going to say, okay, well, this is my function. Negative x to the fourth is my leading coefficient, right? Negative 1 is my leading coefficient, and my leading degree is x to the fourth, right? So here, I'm looking at this graph, and no matter how kind of far down I go, it still looks the same. It's just one giant parabola. So that's interesting. And it's also, if you notice, it's also facing downward. So if I go here, my maximum would be this point, and that's a really ugly number, but that's a maximum. And here are my x-intersects, but those are obviously, not the best numbers you want to be working with. So good thing we have Desmos to help, but here we know that it's concave down. And then lastly, let's look at this one. So that's all we can kind of say about that second function. Okay, well, let's look at this one. Let's think about first what similarities it has to the other 2 functions that we were graphing. One thing I noticed right away is that this has a negative symbol right in front, just like function 2 did, right? The polynomial, I shouldn't say function, but so these polynomials are probably going to be, I'm assuming if it has a negative in front, downward concavity. And if you kind of look at this graph, because we can kind of skip ahead, we've already graphed it, it is a downward concavity. So both of these have a negative symbol in front to lead the polynomial, and both of them are concave down. And if you also look at here, we have 0.1x, and anything times x, if x is 0, is going to be 0. So that's why we have 0, 0, which is the origin, as one of our x-intersects. And our other intersect is negative 4, 0, because x plus 4, if you set that equal to 0, you'll get x is equal to negative 4. And here, you can see that there's a degree 3. And I'm going to bring your attention back to this y is equal to x to the third function, because this is a parent function, this green one. And if you can kind of look, especially if I kind of zoom out, it's very similar to what happens in this area. So this area, obviously this part is different because this doesn't go upward, it actually ends up going downward, but that makes sense. These are 2 different polynomials. But here, if you just ignore from here, where negative 1 to the right, so negative 1 to infinity, if you just ignore that, you're just going to see this, which is very similar to this x to the third parent function. So And that does kind of make sense, just like our linear. So our x with degree 1 and our x degree 2, which had a parabola where that point, if it was an intersection, it bounced off of that point. And now we have a degree 3, and it does the same exact thing that we would expect a degree 3 polynomial to do at that intersection. So I want you to go through and not only write all of your discussion points and findings, but I need you to split up into groups, and we're going to be doing the rest of these together and kind of determining, okay, well, what patterns do we see? What can we always count on happening that can stay consistent and help us solve? All right. So this kind of goes along with that last page, and it also gives you blank graphs to help you with graphing. You guys can pick a different one if you want, but I'm going to choose just like the first one just to make it easy. P of x is equal to negative of x plus 10 times x plus 7 times x minus 12. So it's asking me to make predictions on how many roots that there will be. And I know that I can take each root and set it equal to 0, to solve for the x-intersect. So I know that I'm going to have 3 intersections, x-intersections. I know my prediction is going to be correct because we've worked with factoring before and graphing quadratics, which if you have 2 solutions for x, like for example, if y was equal to x minus 2 times x plus 7, then you know it's going to have 2 roots at 2, 0 and negative 7, 0. So just a little refresher there. And because some of these numbers are pretty big, it would not be fun to graph this, I can tell you that for sure. So if I kind of zoom in on here, I can see that this graph has 3 x intersections and 1 y intersection. And those are all the coordinates right there. All right, so we're going to go down to the concept developer, and we're going to try to figure out how can I predict a graph. So part 1 is called getting to the root of the matter. We are basically taking a polynomial and figuring out, okay, well, if it's in factored form and not standard form, how do I know the leading coefficient and the power of the degree? Well, if I have something like this, y is equal to x minus 2, x plus 4, and x minus 8. Okay, so then I have 3 possible roots. And if I actually multiply this out, because it's separated by multiplication, I'm multiplying all these terms against each other, right? So if I did x times x, I would have gotten an x squared. If I take that x squared and multiply it against this x, I know that I'm going to get x to the third plus blah, 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 whatever. All right, I don't care about that because that x to the third is the leading term and has the highest degree, so that's the one I'm focusing on. So there is 3 roots here, and it's to the 3rd power, so it makes sense that degree 3 would have 3 roots, just like degree 4 would have 4 roots. But keep in mind, doesn't mean they're all real. And that's my little hint for you for later. And in general, we can generalize that degree n will have n, a polynomial with degree n will have n amount of x-intercepts. I'm going to let you answer number 4 on your own because it's asking, okay, well, can a polynomial of degree n have fewer than n roots? Look at what I kind of start up here and kind of try to connect those 2 ideas. Our part 2 is kind of connecting multiplicity. Multiplicity is, we're talking about the degrees, right? So this x minus 5, the root is 5, and it has a multiplicity 3. This one, x minus 1, we have x is equal to 1, right? So x coordinate 1, 0 is an x-intercept, so that has a multiplicity 1. If I continue, x plus 7 and x minus 7 are both squared, and both of those are actually multiplicity of 2 because they're to the 2nd power. So with that idea, we're going to be answering some questions, and I put the t of x and w of x up at the top right corner just so we can see the functions easily. And it's asking, well, what's true about the nature of the intercept in regards to how it acts with these locations? Well, I have graphed both functions, and this is what they both look like. This is x minus 5 to the third and times x minus 1. As you can see, my roots, I have one at 5, 0, and I have one at 1, 0. And as you can kind of see, if you go to zoom in on this 1, the line goes straight through. And that makes sense because if it's a linear line has a degree of 1, right? So a straight line has a degree 1 variable, and that makes sense to go right through the problem, or through the point. If we go to 5, at this point of intersect, you can see that there's a third degree, right? So it's a third degree root. And as you can kind of see, I know it's hard to tell from here, but I'm going to actually graph y is equal to x to the third. And it looks very similar to this function, this parent function, right at this point. All right, so I'm going to get rid of that. And the same thing kind of happens. So it's multiplicity 3, multiplicity 1, and multiplicity 3 has a x to the third form, and multiplicity 1 has a linear form. And if we look at the graph of wx, which is this one, x minus 7 squared plus x plus 7 squared, we're going to be looking at this blue function. And as you can see, we have -7 and 7 as our roots, and both of these are multiplicity 2, so it actually makes sense that if we zoom in on both roots, we're going to see two parabolas that connect. So at the x-intercepts, we have 7, 0, and at 7, 0, we see a parabola. We see a parabola on both. Parabola kind of bounces off the root, and this has a multiplicity of 2. So it says, what can we find out about even-valued multiplicity? Well, after we've kind of experimented with the polynomials we've been experimenting with in graphing using Desmos, we should have come to the fact that, okay, well, an even value is going to look like a second degree polynomial. An odd-valued multiplicity is going to look like a third degree. And does this hold true for other polynomials from your exit ticket? I'm going to circle this one just so you can kind of include some of your observations. I want you guys to use your own words, your own conclusion, but you should have said yes, it does hold true. I'm going to let you do this end behavior part by yourself. Because this is the part of the analyzation. Jump here, and this is kind of the observation I expected you to complete. So I'm going to draw basically a coordinate plane for each one. Let's start with red. So if we have, when a is less than 0, if we have an even degree versus our odd degree, we're going to have something that kind of looks like this. And this middle part could be anything, but what we're looking for is that, okay, well, it has this end pattern. It looks like a parabola, greater than 0, but there's an odd degree. It's kind of similar, but not really, right? So you should have noticed that a polynomial, we'd have something like this, and again, this middle part might be completely different depending on your polynomial, but essentially it's asking you, okay, well, the end behavior, I'm looking at here and here. The a value that was less than 0, I'm going to change the color to green. I'm going to get something like this. And again, the middle part might be something completely different, but again, we're focusing on the end behavior. And this one's kind of like a downwards parabola. This one's like a downward parabola. If we had an odd degree when a was less than 0, we're going to get something along the lines of this. And again, the middle part might vary. But we're focusing on the end part, so it's going upward here and downward here.